Hey guys, this is SuperTestNet, and today I just wanted to show off my latest invention, which is the SSB Playground. The website is right here, and there's a little button down here so you can view the source code of this invention. This is the GitHub, and all the code is in this index.html file. So, what is the SSB Playground? Well, I'm playing around with the Sighash Single Bug, or SSB, and I've made a little website where you can do that too. In case you've never heard of the Sighash Single Bug, there's a little explainer that talks about what it is. Basically, when you're signing a Bitcoin transaction, you can specify on your signature what parts of the transaction you're signing, and you have 6 options for what you can sign, but one of them is buggy. Two of them are buggy. Sighash Single is buggy, and Sighash Single anyone can pay. Those are both buggy. So this bug only affects legacy transactions. SegWit transactions and Taproot transactions are unaffected. But if you're using a legacy transaction and you sign an input with Sighash Single or Sighash Single anyone can pay, and that input does not have an output at that index level, Bitcoin has an error. What does that mean, have an output at the same index level? Well, let's say you have 3 Bitcoin addresses that you're sending from, and you're sending two Bitcoin addresses. They kind of match up. The first Bitcoin address that you're sending from matches up with the first Bitcoin address you're sending to. The second one down here matches up with the second one down here. But the third Bitcoin address you're sending from doesn't have any match over here, and that's when the bug is thrown. If that happens, Bitcoin has this weird sig hash that it wants you to sign that looks like this. That's what you end up signing, and this bug can cause loss of funds if the key you're signing with holds other funds, and other headaches happen, and it's never been fixed. Well, it's been fixed in Taproot and in SegWit, but it's never been fixed in legacy transactions for reasons that you can read more details about on this webpage. But I figured out just a couple days ago, actually on Christmas, I figured out that it's possible to exploit this bug intentionally. You can make a transaction that intentionally exploits it, and the transaction will inform your Bitcoin script about some aspects of that transaction. I made a little list on here of the things it tells you about. If the exploit triggers, then your script knows that the input position of the UTXO being spent is greater than position 1, or position 0 if you prefer indexing from 0. It also tells you that the number of inputs is at least 2. It tells you that the number of outputs is less than the number of inputs. And if the exploit does not trigger, if you test for it and it does not trigger, which you can do in Bitcoin script, then you know there is an output at the current input position. So it just occurred to me a couple days ago that it's possible to do this form of transaction introspection, and so I started playing around with it, made a bunch of things that restrict the future transactions. Like, you can make an address that says if you're going to spend from this address, your future transaction has to have a certain number of outputs, for example, or a relative number of outputs, where you say it has to have a smaller number of outputs than inputs, or it has to have equality, or stuff like that. So I made these different buttons you can click and then try them out. Yeah, that's the thing. Let's do it. Let's see what it looks like. So I'm going to do, the first one here is called an FTX restriction, which stands for fewer than X. We're going to make a restriction that says we're going to put some money in a Bitcoin address, and you won't be able to spend from that Bitcoin address unless your transaction has a smaller number of outputs than inputs. It has to be fewer than a specific number. So let's do it. Let's click OK. Here is the restricted address. There's a smart contract in this address, which you can explore using the source code. And I'm going to send some money to this. I'm going to send it 10,000 sats using my little testnet faucet here. So there we go. 10,000 sats has been sent to this kind of smart contract thing. I'm calling them restriction addresses. You can also use this faucet. I linked to one from Mempool Space, but I'm using my own. Okay. And then it says enter an address where you want the restriction encumbered sats to go. And I'm just going to send them back to myself. So I'm sending them to this address again. And that's like the default. But of course you can put them wherever you want. You can put in whatever address you want. Okay, so now it's created a transaction that won't work. So I've got a little button down here that you can go try to broadcast this transaction. I'm going to try to broadcast it on testnet 4. Click broadcast. And it didn't work. We got a consensus error. It says the script verify flag failed. there's a signature in here, which is the buggy one that requires the sig hash to be the 0, 1, and all the zeros, and it wasn't that wasn't the sig hash, so it failed. And you can see if we go inspect this, I'm going to run Bitcoin CLI decode raw transaction. You can paste it here. Here's the Bitcoin address. Here's the script. It's in here, the thing that says ASM. This is the signature that it's trying to validate, and this is what is that? I forget. That is the Bitcoin script, which it's not really legible in this format. But this says we're gonna check this signature to see if it validates, and it can only validate for that string of 0, 1, 0, 0, 0, and that sig hash only applies if there is no output at this index, which we're at the first index, index 1 or 0 if you prefer indexing from 0. But there is an output here, so it fails. The signature does not validate, and then the Bitcoin script knows there's an input there, so it fails. It says there can't be an input there, and there is, so the transaction fails. Cool. It knew something it's not supposed to know, but it worked. Now we're going to create a valid spending transaction, and in order to do that, what we're going to do is we're going to add a second input to this, and then the second input won't have an output there, so that's where we're going to put the smart contract, is in the second position, and then it'll succeed. So once again, I'm going to send 10,000 sats to this. 10,000 sats, there's the transaction ID, click OK, and now it wants me to broadcast this transaction, and this one succeeds. So there it went off and was happy. And if we examine that transaction, you can see that there are two inputs in this one, and there's only one output, which is the address that I specified. And the smart contract is here in the second one. There's the signature that only validates if the sig hash is 0, 1, and a bunch of zeros. And in this case, that is the sig hash, because as you can see, there's no matching output over here on this side. So the bug got thrown, and that caused the transaction to successfully execute. Okay, so yeah, that's that one, FTX. I also have one called GTX, greater than X, where you basically just flip it and you say, for this one to pass, there has to be, instead of it's not allowed to have an input or an output at the same position, you force it to have one there, and that means there is a number of outputs greater than whatever that index number is. And so you can tell that, and that's what that one does. And then there's equal to. I figured out that you can do equal to by combining the previous two. If you make your last output say there can't be one here, but the second to last output say there must be one here, the only way to satisfy both conditions is to have an exact number of outputs. And the interesting thing here is, or interesting to me anyway, your signatures don't have to commit to the outputs. They can commit to the number of outputs without committing to the outputs themselves. Fascinating. I think that's really cool. And then, in case you're wondering, is any of this useful? I haven't thought of any really compelling use cases for this. It's kind of just Bitcoin theory. You can do really weird things with Bitcoin, including like checking whether a sig hash is this really weird specific value. I did think of one thing that might be useful, and so I'm going to show you that. We're going to create what I call a cleanup restriction. So this is based on FTX restrictions. Basically just an FTX restriction, because the FTX restriction tells you that there has to be more inputs than outputs, and that means you're consuming more UTXOs than you're creating, which is desirable in this age of much spam on Bitcoin. So I worked on that and kind of fixed it up until I got it to where you can like have a really large number of inputs that it has to consume. I made it so it has to consume 100 inputs and create one. So that's what I'm about to do. I'm going to show that to you. It's going to create one spendable output and then a bunch of opereturns that don't add to the UTXO set, and it's going to consume a bunch of UTXOs. So that's what this little text here is saying. What we're going to do. Here's the restriction address. So I'm going to pay that from my thing. I think it wants 10,000 sats. Is that how much it wants in this one? Yeah, 10k sats. So there we go, 10,000 sats. So there's the money going in. Okay, I funded it. Now it says this restriction will require us to consume 100 plus UTXOs as inputs. And because this is, I'm doing this on testnet, well, actually on mainnet too, I don't just have 100 UTXOs sitting around, or maybe I do, I don't know. But I'm going to make some. I'm going to make some to consume them. So I'm going to send this amount to this address, and then I'm going to make, well, 99 UTXOs, and the script requires us to have 100, so 99 plus the one that we just made will be the 100. Okay, so I need to send to this address, and the amount is 56785. 56785 Satoshis. There we go. That's been sent. So I click OK, and it wants me to broadcast this big transaction. So let's do that. Let's see what that looks like. I'm going to examine it. And this transaction, look at all those outputs it creates. It creates 100 outputs. Those are them. That's 100 different outputs. And this is going to represent a cluttered UTXO set. I've got the UTXO set is on testnet 4 is now cluttered with all these UTXOs. Wouldn't it be cool if we could pay someone to clean that all up? So that's what I'm going to do. I'm going to say where the money should go after I've cleaned these things up. And now I've created a Bitcoin transaction that uses this restriction address, which contains 10,000 sats, uses that as an input and tries to clean up. Well, and first I'm going to only clean up some of those outputs. I'm going to clean up 98 of them, and it's not going to work. So I broadcast this, and the signature fails because I have 99 inputs in this transaction. And I've got 99 outputs, and that's not good enough. There needs to be a smaller number of outputs than inputs, and in this one I am committing to the actual output set, so I can't change that. The only way to satisfy the restriction is to increase my inputs by consuming one more. So that one failed because of the restriction. So now I'm going to click OK, and we're going to make one more transaction. This is the same thing, except there's just one more input in it. It's going to consume the last of those, of these 100 that I made here, or of these 99 that I made here. So I paste it, I hit submit, now it works. And so all those UTXOs that were just, that were cluttering up the UTXO set have now been consumed, and only one spendable output has been created, which is, well, I took most of that 10,000 sats from there and used it to pay for fees, but there's still 5,000 sats left in there. And then all these other ones, those are all op returns. The only way I could figure out how to do this thing was to have an equal number of transaction outputs as transaction inputs. That's what the greater than, that's what the less than thing, that's how the less than thing works. But I could make them all op returns so they don't contribute to the UTXO set. And then only this one gets created. So yeah, you can, it gives you a little success message down here. It says, voila, you created a Bitcoin address that enforced a cleanup restriction, an address that anyone can spend from with its anyone can pay signature, but only in a transaction that consumes 100 plus inputs and creates only one spendable output. And I think that's cool. It's a new way to clean up the UTXO set. You can automatically fund these addresses that pay people to do it. It's something you can do with this new restriction thing I came up with. So anyway, oh yeah, one more thing. I forgot that the money in this thing went into another anyone can spend address. So if we look at this output there, the 5,000 sats is not in my address, it's in one of these anyone can spend addresses. So to finalize this thing, I have to sweep it from there. And so I've got a transaction to do that. And there it is. And so now the money has been swept from the anyone can spend address and went to my actual address, the one that ends in 6UHM, which matches the one on my faucet. So cool, yeah, I successfully did that. Now that also means because the money goes into a anyone can spend address before you sweep it, this also isn't safe to do on mainnet, but I have a proposed solution for that here, so check that out. Anyway, it's good enough for demo. Thanks, hope you guys check out the Sighash Single Bug Playground, learn about the Sighash Single Bug, and have fun.